Let's talk about networking. Not that type of networking, the internet kind. Yeah, that's the one. So this video is going to be part of my operating system development series, but as a matter of fact, most of the things that we're going to talk about are not directly related to operating system development. They're more so relating to networking from scratch, protocols, packets, all that stuff. So I will put a timestamp that you can skip to if you don't care about any of the operating system stuff and you just want to see the networking stuff. But let's start with the operating system stuff. If you followed this series, you've definitely heard of the VirtIO devices. So I've talked about them plenty, and the networking device that we're going to be using today, VirtIO NetPCI, is a lot like those. So we've actually already learned how to set these up because we've done it plenty of times before, and I've even created some VirtIO device functions that can be used to do all the common setup functionality that all these devices share. But before I could use this device, I had to make a couple changes to these functions. First off, I talked about virtqueues, and virtqueues are divided into a command available or used ring, and these are used to communicate with the device once the device is set up and live. We send commands to the command ring, we make the device aware of them through the available ring, and the device tells us that it's done processing them through the used ring. But what I didn't mention is that the device can actually have multiple virtqueues, and I did not support this at the time, so now we need to support it because we're actually going to be using two virtqueues, one to transmit packets and one to receive packets, because networking, of course, is bidirectional. In order to do that, we need to look at the VirtIO PCI common configuration. And here, there's all this data that we haven't really been paying attention to, but we care specifically about the queue select and number of queues. The number of queues obviously tells us how many virtqueues we're going to be using, and queue select is an int16 that we can write to in order to select one of these queues. So whenever we need to send something in the transmit queue, we're going to select Q1. Whenever we want to receive a packet, we select Q0. And as a matter of fact, all the properties under that, but specifically the descriptor, driver, and device, which is just another way of calling the command available and used rings, are going to change to reflect the ones for the current virtqueue. Essentially, we're going to set up multiple virtqueues, and then using the queue select, we're going to select which virtqueue we're working with, whether we're transmitting or receiving packets. And the pointers to the descriptor, driver, and device will point to the correct virtqueues. Now, just to be clear about this naming difference between descriptor, driver, and device and the command available and used, they're the same thing. The descriptor queue is the command ring, the driver queue is the available ring, and the device queue is the used ring. It just so happens that in the VirtIO specification, different versions of the spec call it different things. And in my code, I mostly call them descriptor, driver, and device, but in my previous videos, I have called them command available and used, so I'm using those words. Another thing we care about here is the MSIX vector. I talked about MSIX in my video about input, and this is a way that we can set up a table of interrupts. So we can use multiple interrupts for the same device, which is something we're going to want to do for networking. We're going to want to set up an interrupt for when we transmit a packet and an interrupt for when we receive a packet. The interrupt for receiving the packet is pretty obvious what we're going to be using it for, to process the incoming data from the network. The one for transmitting is going to trigger once the packet is transmitted, and we are going to use it to free up the data that we set up for the packet, and we could also use it to keep track of which packets have been transmitted. With that being said, let's talk about what we're going to be using networking for. Because networking is such a vast topic, I probably want to establish some goals, and the goals that I have towards networking are more or less the goals that I have towards the project overall. These are goals that I've talked about in the past, but I haven't fully established them, so let me go over them again. So I mentioned I would want to run this project on a Raspberry Pi, but for the time being, we're actually running on QEMU, which is an emulator that's running on my machine. Wait, that's not right, hold on. There we go. So that means that all the changes that I make on my development machine immediately get reflected on the operating system because the operating system is being emulated on the same machine. We're also not emulating on a Raspberry Pi device yet. We're emulating on a virtual board called Virt, but that doesn't really matter right now. And it might actually be the topic of the next video, so we'll get to that when we get to that. But the point is, everything's running on one machine, so it's really easy for me to make changes. But eventually, I'm going to want to run this on real hardware, separate from my development machine. And that means I'm not going to be able to easily make changes and have them reflected directly on the machine. Now I can obviously continue doing the emulation while I'm developing, but then it's probably going to be useful to have some sort of networking between the two devices so I can communicate with my operating system once it's actually live on real hardware. Now, the goals that I'm going to talk about here are more long-term. They're not something I have implemented in this video or anything like that. They're more so just a little something that I would love to have in the future, but it doesn't really make sense to even think about these things before I actually have the system running on real hardware. So for the time being, these are just long-term goals that I'm maybe working towards. The first could be some sort of remote logging. In case I need to know what's happening on my machine, then it would be nice to have my machine send the logs directly to my development machine, which I can then use to see what's happening on the system. If there's an error or if something's happening, I can look at it through the log without needing to directly connect to the machine or connect a monitor to it or something like that. It would also be nice to have some sort of app store, and please, Apple's legal team, notice the quotation marks around App Store. It could be some sort of repository where I can upload software that can then be installed onto my operating system, and I can go there to download it and to update it. This would also help me develop other things on top of my operating system without needing to recompile the whole operating system the whole time. And we can actually take it one step further by including a firmware updater. So, and this is very much a long-term process because there is a lot of considerations to be done. We could actually update the operating system directly from a server so that I don't have to flash an SD card every time I make a change to the operating system. And maybe even more long-term, it would be nice to have some remote access so that I can directly access and control my machine from my laptop. And this would actually be a full circle moment where we go from being able to directly control the operating system from my laptop because it's being emulated on it to being able to directly control the operating system from my laptop because I have remote access. Oh well. Another thing I mentioned is I'm a game developer and I'm very interested in making some sort of gaming operating system, which is why I made the launcher for this somewhat inspired in a console games launcher. Specifically, I got inspired by the Wii. So if we're going to have games, then the package repository that we can use to install software would be perfect to install these games, but also it would be nice to have some sort of multiplayer. And I know it's a little bit silly to start thinking about multiplayer when we don't even have games. But as a matter of fact, multiplayer uses a very simple protocol called UDP, so it wouldn't be particularly difficult. We're actually going to be using UDP plenty throughout this video, so expanding that to do multiplayer eventually will be pretty easy to do. Of course, before that, I need to actually make some games. So now that we've talked about the long-term goals that I have for the operating system, let's talk about a practical goal that I'm going to be setting so that I can work towards in this video. We're going to want to have a server running on the local network. In this case, it's actually running on my development computer, but really it could be running anywhere on the network. And then my operating system is going to be able to connect to it and receive data from it. And as a matter of fact, it's been so long since I've written simple code using third-party libraries. So this is the code for it. Well, this and this, because there's two parts of it. First off, we have an HTTP server, and then we have a UDP server. So these are two different servers. I wrote one, then the other, although technically I'm using them both now. And in just a few lines of code, we have a server running. It's incredible. Okay, but we're not going to be doing a few dozen lines of code. We're going to be writing a few hundred lines of code in order to do the networking in my operating system completely from scratch. So say goodbye to the nice code and let's move on. First off, we need to talk about the network stack. Well, let's imagine we're going to communicate with our HTTP server, and it's going to look something like this. We're going to send an HTTP request to the server, and it is going to respond back with something. That something can be HTML, it can be a JSON, it can be plain text. It doesn't really matter, but it's going to respond back with data. So this is done over a protocol called HTTP, or the Hypertext Transfer Protocol. Nowadays, HTTP is actually always used in its secure form, or almost always, which is why it's usually called HTTPS. But we haven't even implemented HTTP yet, so we'll get to the encrypted part of it later on. For the time being, we're just going to be focusing on HTTP itself. The thing is, in order to send an HTTP request, we're going to need to do it through some kind of networking protocol. And HTTP, in fact, is built over TCP, which is the Transmission Control Protocol. Now, you may have heard of this protocol. It's particularly complex, but once you understand it, it's not difficult. It just so happens to be built with a lot of redundancies. And as a matter of fact, the latest version of HTTP, I believe HTTP 3, can actually be built over UDP instead of TCP. But again, let's maybe focus on implementing it in the first place and then focus on the upgrades later on down the line. Now, TCP is going to be handling the actual connection between the server and the client. But how does it know which two devices on the network are communicating with each other? Well, that's done through IP. specifically IPv4. And IP addresses can come in 32 or 64 bits. 32 bits is the IPv4 version and 64 bits is the IPv6 version. So far, I'm exclusively using IPv4. But IP just tells us how to communicate the two computers within the network. We need to have some sort of way of identifying the two computers, so we know exactly which two computers are communicating. And that's where Ethernet comes in. This is the top level of the networking stack, and it simply identifies computers using physical addresses. We'll see what all this addressing stuff means in a minute. And because I am using a VirtIO device that I mentioned before, because this is part of my operating system development, there's also a VirtIO header, but it's actually not part of the networking stack. It's just something that I need to use internally as part of my network driver. And actually, it just so happens that all the values that you need to write to it are 0, so it's empty, but it needs to be there anyway. So ignoring the VirtIO header, the rest of the headers are somewhat in a hierarchical structure, where each of them is built on top of the previous one. And actually, it's a little bit more expensive than that. It looks something like this. And this is just for the protocols that I had to implement in order to accomplish the goal that I set out before of communicating with a server on the local network. Now, IPv6 and HTTPS I haven't implemented, but because they're so similar to IPv4 and HTTP, at least in the way that they work, I'm still mentioning them here. And as a matter of fact, there's a few more protocols that we could implement in the future. And DNS is going to be particularly useful if I want to implement communicating with actual websites on the internet, because it's the service that translates something that google.com into the IP address for Google. But it's not something I have implemented yet. And then there's the network time protocol for time synchronization. But again, not something I have implemented. I don't necessarily have a reason to show the current time on my system, and I don't really use it for anything. So, like I said before, these protocols are all hierarchical. We have the HTTP, TCP, IPv4, and Ethernet, and then an alternative to TCP is UDP, over which we can build other protocols such as DHCP. And then there's also some other protocols that are used for the local network, such as ICMP and the ARP. This is a lot of random letters, especially Ps. So we're gonna go through all these packets, explain how they work and what they look like in a minute. But before we get to that point, the hierarchy that I mentioned is actually used to create a model for the network stack. This model is called the TCP/IP model, and it looks like this. At the very beginning, we have the link layer. This is responsible for the physical communication between devices, and it actually even includes the actual physical communication. Think of cables and stuff. Then we have the internet layer. This is the one that handles the routing to establish the communication between two devices. Then we have the transport layer. This is the one that actually does the communication between the two devices. And finally, we have the application layer, which is built on top of all the other layers before, and it's the one that actually transmits the data that we're going to be sending. So whenever we want to make an HTTP request, the content of the request is the application layer. The actual communication happens in the transport layer. The routing to communicate the two computers happens in the internet layer on a logical level, but the actual physical communication happens in the link layer. Now, there is actually a more advanced model called the OSI model. It is more modern and it can be used as an alternative to the TCP/IP model, but as a matter of fact, they're very similar, and TCP/IP just happens to be a lot simpler to explain. And it's not like we explicitly have to implement these models. I'm just showing them here to explain how all this works. OSI actually divides the link layer from TCP/IP into the data layer and the physical layer. The data layer is the actual physical addressing that I mentioned before and that we will see in a minute, and then the actual physical communication happens in the physical layer. The internet layer stays the same, but it gets renamed to the network layer. The transport layer is exactly the same. And then the application layer gets divided into the session, presentation, and application layer. Okay, that's a lot of information that doesn't seem to make a whole lot of sense. So let's go over it. Let's start with Ethernet. Ethernet sends a header that looks like this. It has a destination MAC address, a source MAC address, and an ether type. Now, the thing is, on a network, devices are identified through their IP. But this is actually not fully unique. First off, your IP changes depending on which network you're connected on. And as a matter of fact, even being connected to the same network, you can sometimes be assigned different IPs. So IP is not really a reliable way to uniquely identify which device we're communicating with. That's where MAC addresses come in. These are hardware addresses, and they're unique per each device. Whatever actual hardware we're using to do the network communication has its own MAC address. So it uniquely identifies our device on the network. Now, the MAC addresses are 6 bytes identifiers, And then we have the ether type, which simply indicates the type of data that we're going to be transmitting with this header. And this is 2 bytes. Let's talk about MAC addresses first. A MAC address is the media or medium access control address. I couldn't actually find a consensus on what the M stands for, and I've gone my whole life without knowing that's what MAC stood for, so I'm good with just calling it the MAC address. It's 6 bytes, and we usually represent it as hexadecimal, so it can look a little something like this. And again, it's the physical hardware address of our computer. Let's use a practical example to think about it. Let's imagine that you invite me over to your house, and so you give me your address. But I've never been to your town, and so I don't know exactly where your street is, let alone your building. So I go to Google Maps and it gives me the coordinates to your house. Now, Google Maps would actually give me directions to your house, not just the coordinates, but that kind of breaks the analogy, so ignore that part. Let's just say it gives me the coordinates to the house. Well, the MAC address is the coordinates, whereas the address that you gave me is more so like the IP address. Technically, your address can change. Your street can be renamed, for example, but your coordinates are not going to change. So even if the IP addresses change, the MAC address is always going to be pointing to the same device. And so the fact that we have to send this header every time that we make a request means that we need to know the destination address and the source address every time we make a request. Now, the source address is simple because it's provided by our own hardware, my VirtIO device or whatever network card you're using. But what about the destination address? We don't really know the MAC address of every computer that we want to communicate with. Do we have to learn it? Do we have to memorize it somehow? Well, not really. We're going to be using a protocol called ARP. ARP is the Address Resolution Protocol, and it has the ether type 0x806. So whenever we make an ARP protocol request or respond to one of these requests, we're going to set the ether type to 0x806. And again, the Address Resolution Protocol is the one responsible for translating an IP address into the MAC address of the computer that currently has that IP address assigned to it. So similar to translating the address to its coordinates. Now, this happens specifically over the local network. The goal that I established for networking in this video is to communicate over the local network, so I haven't implemented it over the overall internet just yet. But as far as I understand it, whenever you want to send a request out into the internet, you send it with the MAC address to your router, and then it handles the translation to communicate with the internet. So for the time being, the Address Resolution Protocol is the one that works on our local network to translate IP addresses into MAC addresses. Its header looks like this. We start with a 16-bit hardware type, and this simply indicates what type of hardware we're working with. So the Ethernet protocol that I mentioned before. And as a matter of fact, it's always going to be Ethernet, at least for us. And I believe in the vast majority of cases, it's always Ethernet. So the hardware type for Ethernet is a 1, which means most likely we were going to be writing a 1 to this field. Likewise, the protocol type. This indicates that we're going to be using IPv4. And again, this is almost always going to be IPv4 because as a matter of fact, if we wanted to use IPv6, the 64-bit version of IP addresses, we would actually not be using Address Resolution Protocol at all. We would be using a different protocol. So if we are using ARP, most likely we're going to be using protocol 800 in hexadecimal to represent IPv4. So what we're doing with these two fields is actually establishing which type of address we're going to be translating into which other type of address. Essentially, we're saying we're going to be translating an IPv4 address into an Ethernet address. And because the values of these are barely going to change, I've actually hard-coded them. Now, as if it wasn't enough to have two fields in the header that are almost never going to change, we also have to specify the size of the address for each of them. The hardware size, 6 bytes like we mentioned before, and the protocol size, the 32-bit IP, which is 4 bytes. Again, this is hard-coded because it probably never will change, at least in my system. And finally, an operation code. We send 1 for a request and 2 for a response. We are expected to listen for ARP requests that arrive to our device and respond to them. There's actually a chance that our router will send these requests to us, and if we don't respond, the router might think that we're actually not connected to the network anymore, and it might even reassign our IP address. So most likely we're going to want to respond to these. Also, we're going to want other computers to communicate with us, at the very least just to make sure that our server can respond to us. So we definitely need to be able to respond to ARP requests. Besides the header, we also of course have to send out the actual addresses to be translated and the response to the translations. In the sender MAC address, we're going to send our own address, and in the IP address, we're going to send our own IP address. Then when we're making a request, we're going to want to fill out the IP address for which we want the MAC address, and we're going to leave the destination MAC address empty. In the response, we're going to fill all of this out with the relevant information, and when we receive a response, the destination MAC address is going to be what we're looking for. So we're going to send out one of these requests whenever we want to connect to a server, if we know its IP address, and it will respond back with its MAC address so we can properly make the request directly to it next time. And actually in our Ethernet address, whenever we need to specify the destination MAC address, we're just going to fill it out with all ones, which is to say broadcast to everyone on the network. Because we don't know the MAC address, that's the whole point, to find it out. So we're going to send it out as a broadcast. Okay, so we've talked about how to translate IP addresses into MAC addresses, but we haven't talked about IP addresses, so let's do that. This is done with the IPv4 protocol. Like I mentioned before, IPv4 is for 32-bit IP addresses. So the packet looks like this. It's a lot of fields, but let's go over them little by little. Most of them are always going to be either hard-coded or we don't care too much about them. Let's start with the version. It's 4 bits and it just specifies which type of IP this is. So this is IPv4, so it's going to be hard-coded to be a 4. Then the header length. This specifies the length of the header that we're currently looking at. The thing is, it can optionally have some options at the very bottom of it, so we need to specify its length, just so the receiver knows if there's options to parse or not. But we don't have any, so our length is fixed. Then we have the DHCP, or the Differentiated Services Code Point. This is a field that's used to indicate the type of service that we're going to be sending out, but I'm not sure how this is used exactly. I do think some protocols built on top of IPv4 can use it, but I don't know how often it is used in modern networking or if it's just a legacy field that's not really used all that much. But I don't really do anything with this field. We can just ignore it for the time being. Then there's the explicit congestion notification. This is used to handle network congestion. Again, not something I have really implemented. Then we have the total length. This is 16 bits and it indicates not only the length of the IPv4 header, but also its payload, so the entire length of the packet. That is ignoring the Ethernet header that we sent before this one, but that one is not counted here. After that, we have another 16-bit field called identification. This is used to uniquely identify fragments of packets, because packets can actually be fragmented, but we don't really do that, so we don't use the identification field. Then there's 3 bits for the flags. Honestly, it feels like it shouldn't have been 3 bits. It feels a little bit overkill because really they only indicate one thing, whether the data is fragmented or not. The first bit is reserved, so it should always be 0. The second bit indicates that the fragment cannot be fragmented, and the third one indicates if there are more fragments. So 3 bits to give out what I think is 1 bit of information, but I'm not sure. Like I said, I haven't implemented anything that has to do with fragmenting, so I could be completely wrong about this. And then we have the 13-bit fragment offset, which indicates the offset of this fragment. Okay, let's move on from fragmenting because I'm talking about things that I have not implemented. Then let's talk about the time to live. The time to live is used to indicate the lifetime of a packet, but it's not really something I'm using. I have hard-coded it to be 64, but again, I'm not really too concerned about this field. Then we have the protocol. Finally, a field that I'm actually using. This one indicates the type of protocol that we are building on top of IPv4. For example, I said before that we can send TCP or UDP packets. And for HTTP, we're going to want to send out TCP packets. So in that case, we would set the protocol number to 6. In the case of UDP, we're going to want to set the protocol number to 17. Now, we'll see these packets when we get to them, but the protocol is established here. Then we have the checksum. Now, a network is almost by definition unreliable. Sometimes packets can be dropped, or maybe even some of their data can be corrupted. So in order to verify the integrity of the data, we have a checksum, a calculation that we do in order to make sure that all the data that we are receiving is correct. We'll look into how it works in a minute. Then we have the source and destination IP addresses. These are the 32 bits addresses that we use for routing. So here we simply identify our computer with the source IP and where we're sending our packet to with the destination IP. IP addresses are 32 bits, but for the most part, they look like this. For example, 192.168.1.1, which is an IP address on a local network, which usually would correspond to the router on that network. In order to encode it into a 32-bit value, we do binary shifts on each of the numbers. The first one by 24 bits, the second one by 16, the third one by 8, and the last one written as is. So just like that, we can translate this more readable IP address into a 32-bit value. And of course, we can do the opposite to read back the address into a readable format. Finally, let's talk about the checksum. Like I said, it's used to verify the integrity of the packet that we're sending out. So in all of these fields, we're writing a bunch of bytes. What we're going to be doing is we're going to add up pairs of bytes, so 16-bit values, and that is going to give us a final sum. And then we're going to do a binary NOT operation on it. So let's look at this number in binary. It's all these zeros and ones, and the NOT operation is going to write a 1 where it finds a 0 and a 0 where it finds a 1, inverting the value. So that is our final checksum. That's what we're going to be writing in the checksum field. So we are going to do this checksum calculation whenever we send out a packet. And of course, when we're doing this calculation, the checksum field is going to be 0. If it's not, we have to zero it out because it's not calculated as part of the checksum. So we're going to do this calculation and write it out in the checksum field. And whoever receives our packet is going to do the same calculation and make sure that the calculation that it has done and the checksum field match. If they don't match, then it knows that either we made a mistake when sending the packet, or while the packet was being transmitted, some type of corruption happened, and either the whole packet didn't arrive or some data was changed, and so it mostly will ignore the packet. Now, the checksum calculation is actually used in a lot of different packets, and it more or less looks the same. So now we have Ethernet, we have IPv4, and like I mentioned, what comes after that is either UDP or TCP. There's a few more it could be, but those are the two main ones. So let's talk about UDP, or the User Datagram Protocol. Now, we just talked about how the network can have issues. For example, the network might be a little slow, or maybe we're running our perfect redacted OS operating system and everything works very well, but on the other end, the server is running Windows and so it crashes because it is an inferior operating system. So whatever protocols we use to communicate between our computer and a server, we probably want them to be reliable, right? Well, yeah, but that's not the case for UDP. UDP is actually very unreliable. It does not do anything to make sure that the packets get received. It just sends out packets, and if some packets don't make it, or if maybe they make it but their data is corrupted, the checksum calculation doesn't work and so the packet never gets processed, that's fine. We can afford to lose a few packets. And I mentioned this type of protocol can be used for gaming because in gaming, it doesn't matter if you drop a couple packets. Maybe it will show us lag. Maybe things won't work exactly as you expect them. But it's okay if a couple packets get dropped every once in a while. So we don't need a lot of reliability. Okay, let's look at what the protocol actually looks like. It has this pretty simple header. It starts with the source and destination ports. Now, we have source and destination physical addresses or MAC addresses. We have source and destination IP addresses, the logical addresses. And now we also have ports. Now, the port is a 16-bit value. Now, these are logical ports because on a computer, you can actually have multiple things running. Think of how you can open multiple websites or even have multiple servers running on the same computer. But each of those is going to be connected to a separate port. Whenever you need to make a unique connection between your computer and another one, you always use the same port. And as a matter of fact, when we make requests using a specific source port, we can actually receive responses on that port. For example, our client or our operating system can be using port 8000 to communicate with a server that has an HTTP server running on port 80. But at the same time, our client can communicate with a different server, which also has a server running on port 80. And in that case, it's able to communicate with both because it uses a different source port for each. For one, it can use port 8000, and for the other one, it can use port 8001. And now, whenever one of the servers sends a response, we will know which one it is based on the IP and MAC address, but also based on the port that's receiving that information. If we receive that information on port 8000, then we know it comes from the first server. If we receive it on 9001, we know it comes from the second server. Then we have the length. And again, much like IPv4, this is not just the length of the UDP header, but also of the payload that we're going to be sending with it. And finally, the checksum. Now, the checksum here is a little bit different from the IPv4. Actually, the way that it's calculated is exactly the same, but it also includes a couple fields from IPv4, for example, the protocol, into its calculation. So we need to also pass those to calculate the checksum. Finally, after that, we just have the data. And this is the actual payload that we're going to be sending out. Now, the protocol itself, like I said, is not actually transmitting any useful information. All the protocols that we've seen so far simply are used to establish how we're going to be communicating between two devices. The payload is going to be the actual communication happening. Okay, now that we've established what UDP looks like, let's actually use it. So I mentioned before we have a server running on the local network and we want to communicate with it. So we're going to be sending out a packet in 3 layers: the Ethernet header, the IPv4 header, and the UDP header, as well as some payload that we want the server to receive. So in order to fill these out, we need to know a bunch of information. First off, what's the IP address that we're going to be sending it to? Then what's the MAC address? And finally, what's the destination port? Well, let's answer them one by one. First, the destination port. This is hard-coded. You kind of have to know which port you're communicating to. And for example, like I mentioned before, if we're doing an HTTP connection, then we're always going to be communicating with port 80, unless we explicitly specify a different port. So my server is running on port 8888. So that's the destination port that we're going to be using. Then for the MAC address, we could use ARP, but we don't know the IP address, so instead we're going to be sending this out as a broadcast. Essentially, we're going to be sending our packet to everyone on the local network, and the server is going to be able to respond. We do this by setting the IP address to whatever the IP address for our local network looks like, 192.168.1. something, and that something is going to be 255, which is to say to everyone on the network. And likewise, the MAC address is going to be set to all Fs in hexadecimal or to all ones in binary, which is to say to everyone. So now our computer is able to communicate with our server. We can send out a packet with a payload such as even just hello, and the server will receive that hello, and we can actually make it respond to us. So it's going to respond with world, but that response is never going to arrive. And the reason for that is we haven't exactly connected to the local network. Now, because we are on QEMU, my host computer shares its network with the guest operating system. So I never had to do any kind of connection to the router or anything like that because it's automatically done for me by QEMU. But we're not officially on the network, so to speak. So when the server goes to respond to us, it doesn't know who exactly to respond to because our computer is not really connected to the network, which is why we never receive a response back from it. Because not only do we not know our destination IP, but actually, what's our source IP? We don't even know that. Our source MAC address, we can get it from the hardware. The destination port, we can hard code it to whatever we want. But the source IP, we can make it up and send a broadcast, but that's not exactly correct. And like I said, we're not going to be able to read a response back. So we're going to need to officially connect to the network. And that's where DHCP comes in. DHCP is the Dynamic Host Configuration Protocol. It is the protocol that we're going to be using to communicate with the router and get an IP address on the local network assigned to us. Once we have this, we'll actually be able to communicate with our server, and it will be able to communicate back to us. So if we are connected to our local network, chances are there's a router somewhere, and the router has a DHCP server on it. Now, this technically doesn't have to be this way. The DHCP server can be separate from the router, but if that's the case on your network, then you probably know more about DHCP than I do. In the vast majority of cases, the DHCP server is going to be on the router itself. So what we're going to be doing is we're going to be sending out a broadcast called a DHCP discover. We don't know where the router is, so we send it out as a broadcast, and the router hopefully will respond with something called a DHCP offer. So we're essentially saying, we're on the network, we want an IP address assigned to us, but we don't know who to ask, so we're asking everybody. And then the router responds, I'm the one responsible for giving you an IP address, and I'm offering you this local IP address. So it makes an offer to us. We receive this offer, and we can respond to it with a formal request for it, essentially asking, okay, now I want you to please give me the IP address that you've offered me. And if everything goes well, then it will respond back with an acknowledgement. So we send 2 packets, it sends 2 packets back, and now we should be connected to the local network. What do these packets actually look like? Well, they look like this. Again, it looks like a lot of information, but let's go over it little by little. It's not all that much. Let's start with the operation. It's 1 for request. Then, much like with ARP, we're going to have to specify the hardware type 1 for Ethernet and hardware length 6 for a 6-byte MAC address. Then we have the hops field. This I believe is used for more complex stuff that I'm not doing. If I'm not wrong, it's for relays, but yeah, like I said, not using this value. It's always hard-coded to be 0. Then we have a transaction ID. The transaction ID is used to uniquely identify the sequence of 4 packets that I mentioned before. This should probably be a random number, but for the time being, I have hard-coded it because I'm always sending out the same transaction ID. There's a chance this is actually causing issues with DHCP requests, especially if I try to make multiple ones very close together to each other, like when I start the operating system multiple times while I'm testing something. So maybe I should be using a unique number here, but for the time being, it's hard-coded. Then it indicates how many seconds have elapsed. I actually hard-code this to be 0 in both the discovery and the request. And so far it's been fine, so I don't think it's used, or at the very least, it's not that important. Then we have the flags. For the flags, I'm only sending out 1 bit, which indicates we're broadcasting out this information. Then we have space for 4 32-bit addresses. The first one is the client IP. That is our IP address on the local network if we happen to already know it. The thing is, DHCP works on a lease system, so we request an IP address, but it's given to us for a specific amount of time, that is the lease time. So if we want to keep it for longer than that, we have to renew our lease. And in order to do that, we just make another DHCP request. And we can do that already knowing our client IP. If we don't know it, instead we just write 0. Then we have a field called your address, which is the one that the server is going to respond with that contains the IP address that it is offering us on the local network. Now, at the time that it does this offer, it hasn't yet assigned it to us. We have to make the request, but this is so we know what IP address we're going to be given. Then there's the server address, and the server address should be the server address for the DHCP server, but as a matter of fact, this information sometimes comes in empty. At least that was the case in my network, and there's another way of getting that address eventually. And finally, the gateway address, which if I'm not mistaken is used for relays as well as hubs, but I'm not doing any of that, so I just ignore this one. This is the header of the DHCP packet, but after that, we have a few more fields, like the CH address or the client hardware address. This is where we're going to write our MAC address. Then we have sname, which again, I believe is used for relay, so I'm not looking at this field at all. I just have to include it. Then file, which I believe is used for network booting, but I don't do any network booting, so again, just ignore this one. And finally, the options. We do want to take a closer look to the options because we are going to be using them to actually do the request. So the options always start with a magic number, which is in hexadecimal 63825363. We always put this at the beginning of the options to identify this as a DHCP packet and to identify where the options start. After that, we have to encode each of the options like this. The first of those numbers is the type of option that this is. For example, 53, which is the DHCP type. Essentially, which of the 4 packets that I mentioned before this is. After that comes the length of this option, just 1 byte, and then the actual option itself. In this case, it's 1, which stands for DHCP discover, the first of the 4 packets, the one that we're going to be sending out in order to let the router know that we're on the network and we want an IP address assigned to us. When we receive the address, we expect to find a DHCP type of 2 for the offer, and we're going to send back a 3 for the proper request, at which point we're going to receive a 4 for the acknowledgement. So like I mentioned before, the server address sometimes is not found in the server address packet of the DHCP server, and again, I believe the server actually has a different meaning here. And so we're actually going to use these options to encode both the type of DHCP packet that this is, but also the IP address that we're requesting, or even to read back the IP address for the DHCP server once we receive an offer. Most likely that will be encoded in the options and not in the server address. Okay, so once we've done that connection between our DHCP server, or our router for simplicity, and our computer, then we should officially be on the local network. But before we can actually begin communicating on the local network, we're going to have to make the other computer also aware of us. This is where ICMP comes in. ICMP stands for the Internet Control Message Protocol, and it's a much simpler protocol. If you've ever used ping, then ping actually relies on this protocol. We're going to want to respond to ICMP requests in order to let other computers know that we are active. Now, actually, it might not be necessary to implement this in order to communicate with the server, but I implemented it just in case. And also, implementing this means that I can use ping from my host computer to know if my guest computer, once I actually have it running on real hardware, is active. So the header for this one looks a lot simpler. First off, it has a type. The type is 8 when we're making a request and 0 when we're responding. Then we have the code. This is the ICMP subtypes because there's different types of ICMP packets which have different meanings, but I have hard-coded this to be 0 because I only want ICMP for ping. And I don't really want to send out pings, I just want to receive them and respond to them. Then we have a checksum, which is calculated like we have calculated checksums so far. Then a sequence and an ID. Now, the ID is used to uniquely identify the transaction that we're making, the current connection. If you've used ping, you know that it actually relies on sending out multiple packets and seeing how long it takes for the server to respond to them. So the ID is used to group all of those packets together and the sequence to indicate the sequence of packets. After that, there's a payload. This, I believe, does not have that much importance, but it is usually filled out, and when we respond to an ICMP request, we are expected to send back the same payload. That way, whoever sent out the request knows that we responded correctly. Okay, so with all that, finally, we're able to properly communicate with our server. Now we can, again, broadcast out our UDP packet saying hello, and the server will pick it up, respond to it with the word world, and we will actually receive that. But this is not very interesting. I said we were going to be doing HTTP requests, so let's do that. In order to do that, we're going to need to implement TCP. Now, the header for TCP is not particularly complex, but the TCP protocol is quite complex. Like I said, it's not difficult once you get the hang of it, but you need to understand what's happening here. So much like UDP, we start with a source port and destination port. But after them, we have a sequence number and an acknowledgement number. We're going to see how they work in a minute, but TCP is actually meant to be synchronized. It has a bunch of redundancies and checks built in to make sure that all the data that needs to be transmitted actually makes it to its destination. That's where the sequence and the acknowledgement comes in. These are two numbers. The sequence is our own number, and the acknowledge is the servers or whoever we're communicating with, their own number. And we need to keep track of these numbers and update them as needed in order to keep synchronization between us. I know this doesn't make a lot of sense, but we'll see it in practice and hopefully it will make sense then. After those two numbers, we have the data offset. And our TCP header actually can have options in it. So it makes it a variable length. The data offset indicates where the actual payload of the packet starts. Then we have some reserved bits that we don't need to look at. And then we have flags. There's a lot of flags, all of which are used at different points in TCP, so we will look at them when we actually understand how the TCP connection works. For now, all we need to know is we have 8 bits of flags. After the flags, we have window. And again, window will make sense once we understand sequence and acknowledge, but the way that TCP connections work is we send out a bunch of data and we expect the server to acknowledge that data. Likewise, it will respond with its own data and we have to acknowledge that. The window simply indicates how much data we can receive before we have to send out an acknowledgement, or how much data we're going to send before we have to send out an acknowledgement. Then we have a checksum. It works in the same way as a UDP checksum, meaning that it's a checksum of the TCP packet, its payload, but also the IP addresses and the protocol from the IPv4 header. After that, we have an urgent pointer, and one of the flags is an urgent flag. And if that flag is set, then we have to specify the urgent data that is being sent. I don't know what this urgent stuff is used for. From my understanding, it's not really used in modern networking, so mostly just ignored for the time being. Then we have some options, which also can be used to send out extra information, but we're not doing that, and we're not acknowledging any extra information that's being sent to us. And finally, we have the payload. In case of an HTTP request, that payload is going to be the actual HTTP request. Okay, but sequences, acknowledgements, windows, flags, what does any of this mean? Okay, let's go over it. First off, let's look at the flags. Like I said, there's 8 bits representing 8 flags. First, we have the CWR. It's the congestion window reduced. Again, it's used for handling network congestion, which is not something I'm doing. So this one we're not going to really be looking at. The next one is called the ECN echo bit. And again, I think it has to do with network congestion, so we're going to ignore it. And then we have the urgent bit. This is the one that I mentioned for the urgent pointer, but I also mentioned that we're not really using that, so another one that we're ignoring. Okay, finally we get to some bits that we're actually doing something with. First is the ACK. Sorry, the ACK, or acknowledgement. And like I said, it's very important that we acknowledge the data that we're sent. So part of doing that is the acknowledge number that I mentioned before, but also the acknowledge flag. We'll see how we use them in a second. Then there's the push flag, or PSH. This is used to specify that on top of sending the packet itself, we're also sending some data, because we don't always send data. Again, we'll see it once we see the protocol in action. Then there's the RST, or reset. Whenever we have an error, we're going to be sending out a packet with a RST, essentially to reset the connection. Because like I said, the TCP connection is meant to be synchronized. Whenever there's an error, and that synchronization is either broken or we need to break it because of the error, then we send out a reset flag to let the other computer know. Then there's the SYN, or synchronization. And this is probably going to be used in the first few packets that we send out in order to begin the synchronization process. We're going to be seeing how the synchronization process starts, but yes, most likely the first packets are going to contain the SYN flag. And at the end, we're going to have the FIN, or FIN, which stands for the finish, which closes the connection. So just to recap everything that we've talked about, we're going to open a connection with another host with a SYN flag. We're going to push information with the push flag. We're going to acknowledge information that we receive with the ACK flag. If there's a problem at any point, we're going to use the reset flag. And once we need to close the connection, we're going to use the FIN flag. So how do we actually do this? Well, the short answer is she SYN on my ACK till I FIN. Okay, no. Let's look at it this way. We have our server and we have our computer. And this time we're not going to be communicating with UDP, but rather with TCP, and specifically with HTTP. Even though we haven't looked at that protocol just yet, this is how we're going to be doing the connection between them. So the first packet that we're going to send is this SYN packet. That's the only flag that we're going to be setting. We're going to set the acknowledge number to 0, and we're not going to send a payload. And then we're going to set a sequence number. This should be a random number, but for the time being, I am hard-coding it to 0. I don't have a random number generator for the time being, even though I probably should implement one and use it in all the places where I've said we should be using a random number, but so far I have hard-coded it. But hey, baby steps. So this is where I actually explain the sequence. As we do this communication between the server and the client, we're going to be sending bytes back and forth and packets back and forth. The sequence number indicates how many bytes we have sent, and the acknowledge number indicates how many bytes we have received. So the synchronization happens because the sequence number should match the acknowledge number we receive from the server. And likewise, the server's sequence number needs to match the acknowledge number that we're sending out. If at any point these don't match, then most likely there's been a desynchronization error of some sort, and we need to reset and try again. But again, we're not really supposed to start at 0, we're supposed to start at a random offset. And actually, the process that we're currently doing, called a three-way handshake, is specifically about synchronizing our sequence number so that I can tell the server what my initial sequence is and it can tell me what its initial sequence is. So I'm going to be sending out this packet with my initial sequence, no acknowledgement because I haven't received anything from the server, and no payload because I'm not actually sending any data. The server is going to receive that and it's going to respond back with a sync and acknowledge flag. Now, this doesn't mean that it's acknowledging our sync. Well, the acknowledge part means that. But the sync part means that it itself is sending its own sequence number, so it's performing its side of the synchronization. It's going to send out its initial sequence number, which for my example here is also a 0, and also acknowledge our data. Now, the acknowledgement usually is supposed to be the size of the payload that it has received, but it hasn't received anything. But even then, if I'm not mistaken, the acknowledgement really indicates the next byte it expects to read from us, and so it points to a 1. Even when there's no payload, it increases the acknowledgement number by 1. So we sent out 0, it received 0, and now it expects us to respond with 1. So that's why it sets its ACK number to 1. And again, it does not send a payload. We receive this packet from the server, and we send out our own acknowledgement. Now you can see we have increased our sequence number, because we're now in the next step of the sequence. And likewise, we're also doing the same thing and acknowledging the packet that it has sent. It has no payload, but we still increase our acknowledgement number by 1. At this point, we've done what's called the TCP three-way handshake, the synchronization process where we tell each other our sequence numbers, and so we can consider ourselves to be synchronized. So now we can actually begin with the HTTP part of this. We're not going to look at what the HTTP protocol looks like just yet. We're going to look at that later and simply continue looking at the TCP protocol itself. So we're going to send out a push and acknowledgement. Now, the acknowledgement here is not acknowledging anything that we received from the server because the server hasn't sent out any new information, but TCP requires constant validation, so we need to send it out. And then we also send a push because we're telling the server that we're also sending some data that it needs to read. Now, our sequence number actually did not increase. And the reason for that is whenever we send a packet that's just an acknowledgement, we don't increase the sequence number because we haven't sent out any new information. And finally, the payload is going to be the HTTP request. Again, we're going to look at what it looks like in the future, but all we need to know about right now is it has a length of 72 bytes. So the server receives this packet, and at this point, it acknowledges the packet. Its sequence is increased because so far all it sent out is the sing, and so now it's sending the next step of its sequence, which is just a response to what we sent out. And likewise, it acknowledges that it received the initial 1 plus the 72 bytes of the request that we sent out. So it's acknowledging that it has received 72 bytes plus the one that it had already acknowledged before, with a total of 73. And you can see it does not send a payload back. This is because it hasn't yet processed the HTTP request. This is simply telling us that it has received the request. Because the connection stays open, it can actually send back the data at some other point. And so at this point, it is internally processing the HTTP request, creating its response, and finally it's ready. So it pushes out new data. Its sequence has not increased because its last packet didn't send out any new information, it simply acknowledged what we sent. And its acknowledgement also has not increased because we haven't sent anything new. And then it sends back an HTTP response of a length of 178 bytes. And for the last step, we're going to acknowledge that we have received this information. Our sequence number is now 73. It used to be 1, then we sent out 72 bytes, so now it's 73. And our acknowledgement number has also increased. It used to be 1, and then we acknowledged 178 bytes from the server, so a total of 179. And likewise, we don't need to send any new information, so we don't send a new payload. So at this point, we've done the HTTP section of the TCP request, and we're done communicating with the server. So now it's time to close the connection. We're going to do that by sending out a fin, or a finish, as well as an acknowledgement. Our sequence has not increased because the last time all we sent was an acknowledgement and we haven't sent any new information since then, and we haven't received any new information, so again the acknowledged stays the same. Likewise, we're not sending any new information, so we don't send a payload. The server is going to acknowledge that we're closing the connection with the same sequence number because it hasn't sent out any new information, and an acknowledgement of 73 plus 1. So the acknowledgement that it was before plus the information that it has just received on finishing the connection. So 74. And then it is going to send out its own finish and acknowledge. Again, with the same sequence and acknowledgement because no new information has been sent from us. And finally, to finish fully closing the connection, we're going to acknowledge its finish. And again, it's going to be the same acknowledge as before plus 1 because we have received this extra bit of information, the same sequence and the same payload. Well, our sequence has increased because we sent out a fin and no payload. So at this point, the connection is closed. A somewhat good analogy for understanding this whole TCP process is ordering a pizza over the phone. So first off, we send the SYN, which is the same as just calling up the pizza place and saying, hello, I would like to order a pizza. At which point they acknowledge our response and say, yes, we sell pizzas. So then we acknowledge their response because apparently we talk like robots because of course we are talking like robots. This is not really about pizzas, it's about TCP. So we say, great, I'm happy that you sell pizzas. And that's the handshake part of it. Then we make the actual request. We say, I want a large pepperoni pizza. At which point they respond back, not with the pizza itself, but rather by saying, got it, we will start making your pizza now. And apparently we are repeat customers at this pizza place because they don't have to ask for our address or our payment information, they already have it. So after some time, they actually deliver our pizza to us. And that's the push and acknowledgement that the server sends with the HTTP response. At which point, we receive the pizza and we tell them, thank you, I have received the pizza. At which point, we say goodbye to the pizza delivery person. I know the analogy kind of breaks down because in real life you don't talk like robots, and also you most likely will be making the order to one person and then receiving it in person with someone else, a delivery driver, but hey, it's the best I could come up with. Now, this is what it looks like when a TCP connection goes well. But I mentioned before, what if our server is running on Windows? But what if it goes wrong? So we send out a sync and the server crashes. It never responds with its own sync or acknowledgement. So actually, the way that TCP is built, we can actually retry this. And if we retry this a bunch of times and it never responds, then we can just assume that the server is down or something's wrong. But there's a chance that the server will actually recover and eventually be able to receive that last repeat packet that we sent and respond to it. So just like that, we can see that TCP has some reliability built into it because we have the ability to send packets multiple times if they don't get acknowledged until hopefully they do or we time out. But what if you're developing networking completely from scratch on an operating system that you made yourself and, for example, you send out the wrong acknowledgement number because you're still learning about how all this stuff works in TCP? Or maybe because of endianness differences, you send out the wrong checksum. Well, in this case, the server is either never going to receive the packet or receive the packet and realize that it doesn't really make sense because we're not synchronized anymore. Or likewise, maybe the server responds to our old packets that we sent back, but it wasn't able to process until now. This is actually something that happened to me quite a lot, in which I was sending out new requests, but the server was responding to old requests. And even shutting down the server was not enough to fix this. Restarting the computer was really the only way to fix it. But also, of course, the other solution would be to send out a reset. And in the reset, we're just telling the other server, hey, listen, we've detected a problem at some point, so let's just forget this whole thing. And at this point, the connection is considered severed. Great, so that's TCP. Hopefully I made it simple enough to understand. Let's move on now to HTTP, the actual protocol that we're going to be using to do communication. Well, every other protocol that we've seen so far had some nice little fancy headers with specific sizes and specific values. HTTP doesn't use any of that, it uses text. This was disappointing. And I know text is technically easier for us humans to read, but I had to build a bunch of text parsing functionality into my operating system in order to be able to send out HTTP headers and specifically to receive HTTP headers. So that wasn't very nice of them. I do think later versions of HTTP may use binary headers, but I'm not entirely sure on that one. And even if they do, I believe they use compression. So if I didn't implement text parsing, I would eventually have to implement compression and encryption. So I guess this is the lesser of two evils. So this is what an HTTP request looks like. The GET indicates the type of operation that we're doing. We're getting information from the server. Then we indicate the version of HTTP that we're using, in our case 1.1. Then we specify who we're sending this request to. And this is not the MAC address and not necessarily the IP address, but actually the URL that we're making the connection to. This request I actually got from a curl request that I did in order to see how a TCP connection is made. So it's not one done by my operating system, it's one done by curl and made on the same machine that the server was running on, which is why the host is localhost. Then we have the user agent. It identifies where we're making the request from. It's curl in this case. And finally, the type of data that we're willing to accept back from the server. In our case, we're specifying that we're willing to accept whatever it sends. And then the server is going to respond with something like this. Its own HTTP version, 1.1 as well, then a code 200, which means okay. There's also other codes like 404 for not found or 500 for server error. But if everything goes right, we expect to read a 200 here. Then it tells us which type of content it responded to. We said we accept all kinds of content, but specifically the server is responding back with text plain, meaning just plain text. Then it tells us the current date. That's nice of it, I guess. Then a keep alive connection, which, if I'm not mistaken, means that we can actually send out more HTTP requests to request more information from the server, and it has a timeout of 5, which is what the next part indicates, the keep alive timeout 5. Then it indicates the transfer encoding, and it indicates it as chunked, which means we could actually be receiving the data in chunks in different packets. So then we have the actual data. We have the double new line, which is how we know that we're done with the header and we start with the actual data. And after that, we get that B, which is actually a hexadecimal, to indicate we're receiving 11 bytes of information. That's our hello world data in 11 bytes, one for each character that it's sending out. So the B indicates the size of the chunk that we're receiving right now, then the contents of the chunk, and after that, that 0 indicates that it's done transmitting data. There's no more chunks after this one. So that's how we know that the HTTP transfer is done. Okay, so that's our networking established. We've done UDP, TCP, HTTP, ICMP, ARP, IP, RP, RPG. Okay, no, not those. But now let's talk about a couple considerations. First off is endianness. My system is built on ARM, which is little endian. The internet, for whatever reason, we have decided is big endian, which means most of the fields, or at least the ones that are more than 1 byte long, I need to swap their endianness. Otherwise, you get errors, which is why I mentioned a checksum error, because this happened multiple times. I forgot to swap the endianness of some bytes, and so I ended up with the wrong checksum. Then, some considerations about connecting QEMU to the host's network. Like I mentioned before, this should be done automatically, and I do it with a command like this, which actually recently someone made a pull request indicating that the VMnet bridged is actually a macOS only thing, so that's not really needed in Linux. But essentially, it just bridges the connection between the host and the guest. But specifically on macOS, this VMnet functionality is privileged. So QEMU should be signed to include some entitlements that allow it to do this networking stuff, which it's not. And also, we don't really need to go into it right now. It's not really important. But the point is, it won't work on macOS. So as a workaround, we have to use sudo. If we run the qemu command with sudo, we will actually be able to connect to the network. Otherwise, it will have an error. Okay, moving on to debugging. If you're going to be doing any sort of networking development, especially when it comes to packets, use Wireshark. It's a free tool that allows you to inspect the packets that are being sent over a network. It has great filters, it has a lot of information, it can check checksums for you, it can parse the packets. For example, if your checksum is wrong, it can tell you what it was supposed to be. And that's actually how I figured out in a lot of cases I got the endianness wrong. Or if you see that you're sending out a packet with the IP address flipped, that's also an endianness problem. So Wireshark is great for debugging sending packets. And actually, it's what I used to learn TCP. Like I said before, I set up my server with the node server that I showed before. And then I made a request to it using curl, and I just looked at what was happening in Wireshark. And that's how I understood how things should work. And the TCP example that I gave before is based on that one connection. So now that we're done implementing networking, what am I using it for? Well, first off, I connect to the local network to receive an IP. This is done through DHCP. Then I respond to ARP requests and pings so that others can be aware of my presence on the network and communicate with me. After that, processes that run on my operating system can bind themselves to ports, and once they do that, they can send and receive packets through those ports. And then I implemented the server connection that I mentioned before. Specifically, a process can send an HTTP request to my firmware update server. It doesn't really work like that, but eventually will become a server used for firmware updates as well as package management. So it will make an HTTP request to the server and it will receive back that information in a JSON format. I'm currently not parsing this JSON or doing anything with it. All I'm doing is just communicating with it and receiving back this information. Eventually, I will expand it into a proper package management and firmware update server. But how do we know the server's IP? Now, we know how to figure out the MAC address from the IP, and we know that the port has to be more or less hard-coded, and there's a few common ports that are always used for certain connections. So when we make an HTTP request to the server, most likely we will connect to its port 80. But what about its IP? We could hard code it, but then again, anyone else running this on their own machine, or even if my machine changes its IP address, or if I connect to a different network, then I will have to update the server's IP that's hard coded in my operating system. So that's not ideal. Instead, I'm using the HWP protocol. Okay, it's not a real protocol. It's the Hello World protocol. I created it myself simply to find the server on the network without needing to hard code its address. So you remember our Hello World communication using UDP with the server over port 8080? Well, that's what I'm using. I send out a UDP broadcast with the payload hello. The server is going to be listening for UDP broadcasts on port 8080, and if it receives one that says hello, it will respond back with world. And once we receive that response, we will know that we found the server. Now, it is obviously very easy to set up another server that also responds to UDP requests. And so it would be pretty easy to just hijack the whole server process, but we're currently not using it to actually download any information from it, so I'm not too concerned about this. It also only runs on my local network. And I do understand that my last video was about security, and in this one I'm saying, yeah, I don't care if someone can impersonate my server, but it's maybe something to consider in the future, not really right now. For the time being, I control both the server and the client on my local network, so I'm not super concerned about this. So once we've done this HWP connection, the server actually has another HTTP server running on port 80. And now we're able to communicate with it using HTTP, and we actually already have its IP address and its MAC address because it responded to our UDP request and we got them from there. So we can actually skip the ARP step. So that's all I have for networking. Again, there's plenty of other protocols that I'm probably going to want to implement in the future. We technically are not able to communicate with devices outside of our local network. At the very least, I don't think so. So I will need to expand this, but for the time being, that's all. I think my next video will be focused on porting to the Raspberry Pi so that I can actually have this running on, at the very least, QEMU emulating a Raspberry Pi instead of emulating a virtual board, with the eventual goal of running this on a real Raspberry Pi. But that last part depends on, first off, how long it takes me to port it, and second, when I actually get a Raspberry Pi. For the time being, that's all.